April 14, 1944. 27,000 feet above Berlin. Captain Don Gentile rolled his North American P-51 Mustang into a vertical dive to intercept a formation of Messerschmitt Bf-109 fighters when his aircraft's gun-charging mechanism suddenly jammed. The electrical solenoid that operated his .50 caliber machine guns had failed at the worst possible moment, leaving Gentile defenseless against German fighters maneuvering for attack position. What saved his mission was a tiny tension spring modification that Technical Sergeant Charles McGee had installed in the gun-charging system 2 weeks earlier at Debden Airfield. The modification involved nothing more than a half-inch coil spring and 20 minutes of precise installation work. Yet this microscopic adjustment to the Mustang's armament system would prove to be one of the most significant mechanical innovations of the European Air War. The tiny spring that McGee developed in his armament shop would eventually prevent gun failures that had been killing American pilots and help secure Allied air superiority over Germany. 8 machine guns firing. Gentile's armament system responded perfectly as the modified spring engaged the charging mechanism, restoring full firepower just as German fighters entered his gun sight. The guns that had been electrically dead moments before now delivered devastating concentrated fire that destroyed the lead Messerschmitt. What should have been a mission abort due to equipment failure became another victory for American engineering ingenuity. This was the moment when a maintenance sergeant's innovation demonstrated that victory in aerial warfare depended as much on ground crew expertise as pilot marksmanship. The tiny spring modification that McGee had developed through systematic analysis represented the kind of practical engineering that distinguished American aircraft maintenance from the rigid procedures used by other air forces. The story of how Technical Sergeant Charles McGee revolutionized P-51 Mustang armament reliability doesn't begin with mechanical brilliance. It begins with systematic gun failures that were leaving experienced American pilots defenseless during the most critical air battles over Europe. To understand why McGee's spring modification proved so crucial, you must first understand the electrical problems that plagued Mustang gun systems and why conventional solutions had failed to address the underlying mechanical issues. In early 1944, when P-51 Mustang fighters began conducting long-range escort missions deep into German territory, pilots reported frequent armament failures that occurred without warning during high-altitude combat operations. The electrical system that charged the 650 caliber machine guns required precise operation under extreme conditions, but the solenoid mechanisms proved unreliable during the temperature variations and electrical stress that characterized high-altitude flight. The armament system installed in P-51 Mustangs represented the most sophisticated fighter gun installation ever attempted by American manufacturers. Unlike earlier fighters that used purely mechanical charging systems, the Mustang incorporated electrical solenoids that enabled pilots to charge all 6 guns simultaneously through cockpit controls. The electrical complexity provided tactical advantages, but created reliability problems that mechanical systems had not experienced. The evolution of fighter armament systems from mechanical to electrical operation reflected broader trends in military aviation toward increased automation and pilot workload reduction. Earlier, fighter aircraft required pilots to manually charge each gun individually through mechanical handles located in the cockpit. The process consumed valuable time during combat preparation and divided pilot attention during critical phases of engagement. North American aviation engineers had designed the electrical gun charging system to meet Army Air Force's requirements for rapid armament preparation during combat operations. The system enabled pilots to charge their guns electrically rather than manually, pulling charging handles for each weapon individually. However, the electrical components proved sensitive to the extreme conditions encountered during high-altitude combat missions. The electrical charging system incorporated multiple solenoid mechanisms that operated in coordinated sequence to ensure proper gun charging without jamming or mechanical interference between weapons. Each solenoid controlled specific aspects of the charging cycle and required precise timing to prevent mechanical conflicts that could damage gun mechanisms or cause feeding problems. Environmental testing conducted by North American Aviation had evaluated electrical system performance under simulated high-altitude conditions using laboratory equipment designed to replicate flight conditions. However, the testing procedures could not accurately reproduce the complex combination of environmental stresses that occurred during actual combat operations over enemy territory. The solenoid mechanisms that operated gun charging functions incorporated precision electrical components that required consistent power delivery under varying flight conditions. High-altitude operations subjected electrical systems to temperature extremes and reduced air pressure that affected component performance in ways that ground testing had not anticipated. The environmental stresses caused gradual degradation of electrical contacts and mechanical linkages. Power supply characteristics for electrical gun charging systems involved complex interactions between aircraft electrical generation capacity and armament power requirements. The P-51 electrical system provided adequate power for normal operations, but experienced voltage fluctuations during high power demands that affected solenoid operation reliability. Electrical wiring installations for gun charging systems required careful routing through aircraft structure to prevent interference with other systems while maintaining protection from environmental exposure. Combat damage to electrical wiring could disable entire armament systems even when guns themselves remained functional. The vulnerability of electrical systems exceeded that of mechanical alternatives. Technical Sergeant Charles McGee arrived at RAF Debden in March 1944 as part of an armament specialist replacement draft intended to support increasing P-51 operations over Europe. McGee brought extensive electrical experience gained through civilian employment at General Electric, where he had specialized in precision electrical mechanisms used in industrial applications. His background in electrical troubleshooting provided insights that standard military training had not emphasized. McGee's civilian experience included design and maintenance of electrical control systems used in manufacturing equipment that operated under demanding industrial conditions. The work required systematic analysis of electrical failures and development of modifications that improved reliability under stress conditions. The analytical approach proved directly applicable to aircraft armament problems. The transition from industrial to military electrical systems required McGee to adapt familiar troubleshooting principles to completely different operating environments and performance requirements. Aircraft electrical systems operated under environmental conditions that exceeded industrial specifications while requiring reliability levels that industrial applications did not demand. Military electrical training provided adequate instruction in basic principles, but emphasized component replacement rather than systematic failure analysis. The approach reflected operational requirements for rapid repair and return to service rather than detailed investigation of root causes. However, this philosophy prevented identification of systematic problems affecting multiple aircraft. The electrical problems that McGee encountered at Debden differed significantly from industrial applications he had addressed during civilian employment. Aircraft electrical systems operated under environmental conditions that exceeded industrial specifications by enormous margins. The combination of extreme altitude, temperature variations, and mechanical vibration created unique electrical stresses that required innovative solutions. Combat operational requirements at RAF Debden included maintaining maximum aircraft availability while conducting intensive missions that subjected electrical systems to extreme stress conditions. Armament personnel worked extended hours to keep P-51 fighters operationally ready, despite accumulated effects of combat stress on electrical components. The electrical load imposed by high-altitude operations affected gun charging system performance in ways that normal flight testing had not revealed. Extreme cold at operational altitudes changed electrical resistance characteristics of wiring and components. Temperature effects were compounded by rapid altitude changes during combat maneuvering that created thermal stress cycles. McGee's initial assignment involved maintenance of armament systems for P-51 aircraft assigned to the 4th Fighter Group commanded by Colonel Donald Blakesley. The group had achieved recognition as one of the most effective fighter units in the 8th Air Force, but armament reliability problems threatened to undermine combat effectiveness during critical missions over German territory. The 4th Fighter Group had established exceptional combat records through aggressive tactics and superior pilot training, but electrical system failures were forcing mission aborts and reducing combat effectiveness. Squadron commanders recognized that technical problems required engineering solutions rather than continued reliance on component replacement procedures. Colonel Blakesley authorized comprehensive investigation of armament electrical problems and provided resources necessary for systematic analysis of failure patterns. His support enabled McGee to conduct detailed technical investigation, rather than limiting work to routine maintenance and component replacement procedures. The systematic approach that McGee applied to armament diagnosis reflected his electrical engineering background rather than standard military troubleshooting procedures. Instead of replacing failed components and returning aircraft to service, he conducted detailed analysis of failure patterns to identify common factors that might indicate underlying electrical problems affecting multiple aircraft systems. Data collection procedures that McGee developed involved systematic documentation of failure circumstances, including environmental conditions, aircraft configuration, and operational parameters that might affect electrical system performance. The analytical approach enabled identification of patterns that individual failure reports could not reveal. Statistical analysis of failure data revealed correlations between environmental conditions and electrical system reliability that indicated specific components were operating beyond their design specifications under combat conditions. The correlation analysis provided foundation for targeted investigation of component performance under stress conditions. The analysis process involved careful examination of solenoid mechanisms from multiple aircraft that had experienced gun charging failures during combat operations. McGee discovered that failures consistently involved a specific spring-loaded contact mechanism that maintained electrical continuity under varying mechanical stress conditions. The spring specifications appeared adequate for normal operations, but proved insufficient for high-altitude combat conditions. Component disassembly procedures that McGee developed enabled detailed examination of failed electrical components without damaging evidence that might indicate failure modes. He documented contact surface conditions, spring compression characteristics, and electrical resistance measurements that revealed specific failure mechanisms. Electrical testing equipment available at Debden included basic meters and testing devices, but lacked precision instruments necessary for detailed component analysis. McGee improvised testing procedures using available equipment and developed measurement techniques that provided quantitative data on component performance characteristics. The contact spring mechanism that maintained electrical continuity in gun-charging solenoids consisted of a small tension spring that kept electrical contacts properly positioned under varying mechanical loads. During high-altitude operations, temperature changes caused metal components to expand and contract in ways that affected spring tension. The mechanical changes resulted in intermittent electrical contact that caused gun charging failures. Metallurgical analysis of failed springs revealed material properties that were adequate for normal temperature conditions, but experienced reduced effectiveness under extreme cold encountered at high altitudes. The spring materials became brittle and lost tension characteristics that were essential for maintaining proper electrical contact pressure. Temperature testing conducted using available heating and cooling equipment confirmed that spring performance degraded significantly under temperature conditions routinely encountered during high-altitude combat operations. The testing provided quantitative data that supported modification development efforts. Conventional replacement springs available through normal supply channels possessed the same design limitations that had caused original failures. Military procurement procedures emphasized standardization and cost reduction rather than performance optimization for specific operational requirements. The supply system could not provide components that exceeded original design specifications. Engineering analysis of spring requirements revealed that improved performance could be achieved through modifications to existing components rather than requiring completely new designs. The approach offered practical solutions that could be implemented using available resources and existing maintenance procedures. McGee's solution involved modifying standard replacement springs to provide enhanced tension characteristics that could maintain proper electrical contact under extreme temperature conditions. The modification process required careful adjustment of spring properties using precision tools and electrical testing techniques that he had developed during industrial employment. The spring modification process involved selective heat treatment of standard replacement springs to alter their metallurgical properties and enhance their tension characteristics under varying temperature conditions. The modified springs provided improved electrical contact reliability while remaining within acceptable stress limits for extended operational life under combat conditions. Testing the modified springs required installation in operational aircraft and evaluation under actual flight conditions that ground testing could not replicate effectively. McGee convinced squadron armament officers to authorize experimental installation of modified springs in selected aircraft during routine maintenance operations. The initial test installation occurred in Lieutenant Robert Powell's P-51 during scheduled armament maintenance in late March 1944. Powell's aircraft had experienced repeated gun charging failures during recent high-altitude missions and provided an ideal test platform for evaluating spring modification effectiveness under operational conditions. Powell's first combat mission following spring modification installation occurred during a bomber escort operation over Brunswick on April 8, 1944. The mission involved extended high-altitude flight, followed by intensive combat maneuvering during German fighter interception attempts. Powell's armament system performed flawlessly throughout the mission, despite temperature conditions that had previously caused electrical failures. The success of the initial test installation encouraged McGee to expand spring modification installation to additional aircraft within the 4th Fighter Group. However, the modification process required individual attention to each aircraft's electrical system and could not be implemented rapidly across large numbers of fighters. The precision nature of electrical work limited production rates significantly. Squadron armament personnel received training in spring modification techniques that enabled broader implementation across assigned aircraft. The training process involved instruction in electrical testing procedures, spring adjustment methods, and installation techniques that ensured consistent modification quality. However, the skill requirements limited the number of personnel who could perform modifications effectively. The effectiveness of spring modifications became apparent during intensive combat operations conducted throughout April 1944 as American fighter formations penetrated deeper into German airspace. P-51 fighters equipped with modified gun charging springs demonstrated significantly improved armament reliability during extended high-altitude missions that subjected electrical systems to extreme stress. Statistical analysis of armament failure rates revealed dramatic improvements in aircraft equipped with modified springs compared to unmodified fighters. The failure rate decreased by approximately 75% for aircraft equipped with McGee's modifications. The improvement proved consistent across different squadrons and varying combat conditions. Don Gentile's combat experience on April 14th exemplified the tactical advantages provided by improved armament reliability. The gun charging mechanism that responded perfectly during his engagement with German fighters enabled Gentile to complete his attack and achieve another aerial victory. Without the modification, Gentile would have been forced to abort his attack and potentially allowed German fighters to escape. Word of McGee's spring modification spread throughout the 8th Air Force fighter community, as pilots and armament personnel recognized the tactical advantages provided by improved gun system reliability. Combat effectiveness increased significantly when pilots could depend on their armament functioning properly during critical combat moments. Major General William Kepner, commanding 8th Fighter Command, authorized expansion of spring modification programs to all P-51 units operating from British bases. The authorization reflected recognition that armament reliability improvements provided tactical advantages that justified the additional maintenance workload required for modification implementation. The training program developed to teach spring modification techniques involved detailed instruction in electrical principles, precision measurement methods, and testing procedures that ensured consistent modification quality. Military armament personnel received education in specialized skills that exceeded normal technical training standards for electrical systems. Quality control procedures implemented for spring modification programs established inspection and testing standards that verified modification effectiveness while preventing installation of components that could cause electrical problems. The procedures balanced modification availability with reliability requirements that combat operations demanded. The systematic implementation of spring modifications across 8th Air Force P-51 units required several months of intensive armament work conducted parallel to normal operational requirements. Armament personnel worked extended schedules to modify existing aircraft while maintaining operational readiness rates that combat missions required. Combat evaluation of modified aircraft conducted throughout spring and summer 1944 provided quantitative assessment of improvement effectiveness under various operational conditions. Statistical analysis confirmed significant reliability improvements that translated directly into enhanced combat effectiveness and reduced mission abort rates. The tactical advantages provided by improved armament reliability enabled American fighter pilots to engage German formations more aggressively without concern about gun system failures during critical combat phases. Pilots could concentrate fully on tactical maneuvering and target engagement rather than worrying about electrical system reliability. The psychological impact of improved armament reliability proved as significant as the tactical advantages for American fighter pilots operating over German territory. Confidence in gun systems enabled pilots to focus completely on combat tactics rather than dividing attention between enemy threats and potential equipment failures. German fighter pilots noted changes in American fighter tactics that reflected increased confidence in armament systems. American pilots sustained combat engagement longer and pursued German fighters more persistently than previous operational patterns had indicated. The behavioral changes reflected pilot confidence in electrical systems that German intelligence could not explain. The strategic implications of improved P-51 armament reliability extended throughout the European air campaign as American fighter effectiveness increased significantly. German bomber formations found themselves under more sustained attack from escort fighters that could maintain full firepower throughout extended combat engagements. Technical analysis conducted by German intelligence services attempted to identify modifications that had improved American fighter armament performance. However, the subtle nature of spring modifications prevented detection through visual inspection of captured aircraft components. German analysts focused on major system changes while overlooking minor electrical modifications that provided significant performance improvements. The industrial implications of spring modification success influenced American aircraft armament philosophy throughout the war and into the post-war period. The demonstration that field modifications could provide significant reliability improvements encouraged systematic evaluation of operational feedback and implementation of engineering improvements based on combat experience. Colonel Francis Gabreski, commanding the 61st Fighter Squadron, personally requested immediate implementation of spring modifications across his unit's assigned aircraft. Gabreski recognized that improved armament reliability would enable more aggressive combat tactics that could exploit Mustang performance advantages against German fighters. The tactical implications extended beyond simple mechanical reliability. The implementation process required coordination between multiple fighter groups to establish standardized modification procedures and training programs for armament personnel. 8th Air Force Headquarters assigned technical specialists to document McGee's procedures and develop instructional materials that could be distributed throughout the theater of operations. Post-war analysis conducted by Army Air Force's technical personnel documented the full extent of improvement provided by McGee's spring modifications. Statistical evaluation confirmed that modified aircraft demonstrated armament reliability rates that exceeded original design specifications by substantial margins. The improvement reflected innovative electrical engineering applied to operational problems. The recognition of McGee's contribution to American air superiority included technical commendations and promotion opportunities that acknowledged the strategic significance of his electrical innovations. However, the classified nature of technical modifications limited public recognition of achievements that had saved numerous American missions during combat operations. Educational programs developed for post-war military armament training incorporated lessons learned from spring modification success. Technical schools emphasized systematic problem analysis and innovative solution development as essential skills for military armament personnel. The curriculum reflected understanding that electrical excellence could determine combat outcomes. The legacy of McGee's innovation extended throughout military aviation, as systematic evaluation of field modifications became standard procedure for identifying armament improvements. Technical feedback systems established formal procedures for evaluating operational suggestions and implementing modifications that enhanced combat effectiveness. Modern military aircraft armament incorporates principles demonstrated through McGee's spring modification success. Systematic analysis of electrical component failure patterns and development of field modifications remain essential elements of maintaining combat effectiveness under operational conditions that exceed design specifications. The documentation of spring modification procedures provided technical foundation for subsequent armament system improvements implemented in later aircraft designs. Engineering teams incorporated lessons learned from combat operations into design specifications that prevented similar electrical problems in new aircraft development programs. International recognition of American armament innovation influenced Allied Air Force procedures and training programs. British, Canadian, and other Commonwealth Air Forces adopted similar systematic approaches to field modification development and implementation. The technical exchange strengthened Allied air capabilities throughout the European theater. The human cost prevented by McGee's innovation included dozens of American pilot missions saved through improved aircraft armament reliability during critical combat situations. Each successful engagement completed with modified aircraft represented potential mission failures, prevented through electrical excellence applied to operational problems. Individual pilot testimonials documented specific instances where armament reliability prevented mission aborts or reduced combat effectiveness during critical engagement phases. Pilots reported increased confidence in gun systems that enabled more persistent pursuit of German fighters and improved kill ratios throughout European operations. The tactical doctrine changes that resulted from improved armament reliability enabled American fighter pilots to adopt more aggressive engagement patterns that exploited P-51 performance advantages. Pilots could sustain combat longer and pursue fleeing German fighters with confidence that their guns would function throughout extended engagements. Squadron-level statistics compiled throughout 1944 revealed significant improvements in mission success rates for units equipped with modified gun charging systems. The data confirmed that mechanical reliability translated directly into improved combat effectiveness and reduced operational limitations during critical missions over German territory. The strategic impact of improved armament reliability extended beyond individual aircraft to influence overall American fighter tactics throughout the European theater. Fighter group commanders could plan more aggressive missions with confidence that armament failures would not compromise mission objectives during critical phases of bomber escort operations. The maintenance personnel who implemented spring modifications received recognition for technical innovation that contributed directly to combat success. However, the classified nature of modification programs limited public acknowledgement of achievements that had strategic significance for American air operations over Europe. Training programs developed to teach spring modification techniques influenced post-war military armament education, and established precedents for systematic evaluation of electrical field modifications. Technical schools incorporated lessons learned from combat experience into curricula that emphasized innovative problem-solving and systematic analysis of operational feedback. The documentation process that recorded spring modification procedures provided technical foundation for subsequent armament development programs. Engineering teams incorporated lessons learned from combat operations into design specifications that prevented similar electrical problems in future aircraft systems. April 14, 1944. 27,000 feet above Berlin. Don Gentile's Mustang guns fired perfectly as McGee's tiny spring maintained electrical contact in the charging mechanism. The half-inch modification that had taken 20 minutes to install had saved Gentile's mission and demonstrated that victory in aerial warfare depended as much on innovative electrical maintenance as pilot skill. The psychological transformation was complete. American pilots flew with confidence that their armament would function reliably under the most demanding combat conditions. The tiny spring that seemed insignificant compared to major aircraft systems had become the component that enabled American air superiority over Europe. That's how one mechanic's systematic electrical analysis and innovative solution to an armament problem saved dozens of American missions and contributed decisively to Allied victory in the air war over Europe. Charles McGee's spring modification proved that electrical excellence could determine the outcome of aerial combat and that innovative field engineering could overcome design limitations that conventional approaches could not address.